Hello student. Today we will discuss the important small chapter bond. Bond is very much essential in RCC structure. A RCC member can act successfully as a composite member as one unit only when both the constituent materials, steel and concrete, carry the force together. They should act as one unit. The steel can resist any force when the force is transferred to it from surrounding concrete, and this transfer of force is achieved only through the bond. The force which prevents the relative movement between concrete and steel is known as bond. Remember, RCC is three-legged race. The connection between the two persons must be perfect. Otherwise, the two person in three-legged race will not run effectively. So to win the race, there must be perfect bonding between the two legs of two persons. Bond stress is defined as a longitudinal shear stress acting on the surface between steel and concrete. Bond stress is also defined as the intensity of adhesive force per unit of surface area. Bond is due to combined effect of adhesion and friction. Now there are three different types of bond. Anchorage bond for transferring the force from the bar to the surrounding concrete before it is terminated, that is anchorage bond. Then flexural bond, the change in the bar force along its length due to variation in bending moment in this length. The bond force developed is called flexural bond. Flexural bond is one type of development bond. And the third type is development bond. For transferring the force to the bar from surrounding concrete, the bond required to be developed is called development bond. Now let us see what is development length. Anchorage bond stress arises when a bar carrying certain force is terminated. In such a case, it is necessary to transfer this force in the bar to the surrounding concrete over certain length. The length of the bar LD required to transfer the force in the bar to the surrounding concrete through bond is called anchorage length. The length of embedment LD of the bar beyond the theoretical termination point is required so that the bar does not get pulled out. For example, consider a cantilever beam or a cantilever slab. This is a cantilever slab, and to resist tension, as there is a hogging bending moment, tension will be at the top. So main steel is provided at the top. Now if you provide bar up to this point only, what will happen? There is a possibility of the bar get pulled out due to this hogging bending moment. What will happen? This bar will get pulled out, and to avoid this, one should embed this top bar which is under tension to a sufficient length so that it will not get pulled out. So how the development length is calculated, we will see here. Before that, the bond stress depends upon grade of concrete. The design bond stress is given in clause 26 of IS 456/2000. It is denoted by tau BD, design bond stress measured in Newton per square millimeter. For bars under tension, for grade of concrete, and this table is for Fe 250. This is for Fe 250. That is mild steel. M15, M20, M25, M30, M35, M40 and above, and corresponding tau BD values are given in Newton per square millimeter. Remember, this is for mild steel. For deformed bars, that is for torch steel, Fe415 or Fe500, these values given in this table are to be increased by 60%. So, this is for Fe415 or Fe500. So, after increasing these values by 60%, these values are for torch steel, deformed bars. So, these are the values after increasing by 60%. Now, if the bars are under compression, the values of bond stress in the bar shall be increased by 25%. So, if the bar in compression, the value of bond stress is increased by 25%. Now, how to calculate the development length LD? LD is equal to phi into sigma x upon 4 tau BD, where phi is nominal diameter of the bar, sigma 0.87 Fy, and tau BD is the bond stress given in clause number 26 of IS code. Tau BD. This table gives us the value of tau BD. Remember, this table is for bars in tension and for mild steel, and this table is for bars in tension for torch steel, that is Fe415 and Fe500, and if the bars are under compression, increase the values by 25%. Now let us consider one example in which it is mentioned that find the LD, development length, for 10 mm diameter bar. So given point of diameter of the bar 10 mm, it is mild steel, so Fe250 in tension, and grade of concrete is M20. So solution for this, as we know, LD is equal to phi into sigma s divided by 4 tau BD. So phi in this case is 10 mm. This is 0.87. Fy is 250 divided by 4 into tau BD. Tau BD for M20 grade concrete, it is 1.2. You can see here it is 1.2 for bars in tension, and this is for mild steel. So 1.2. After simplifying this, what we'll get, LD is equal to 453, 453.125 mm. Now second problem. Let us consider second problem. Find the development length for 10 mm. So again, given diameter of the bar is 10 mm. Fe415, so it is tall steel. Bar in tension, M20 grade concrete. So for M20, for bar in tension, tau BD value is 1.2, and but this is for mild steel. For tall steel, we must increase, for tall steel, we must increase this value by 60%. So LD equal to same formula phi into sigma s upon 4 tau BD. So phi is 10.87, Fy is now 415 divided by 4 into, as there must be 60% increase, I will multiply 1.2 by 1.6, because for torch steel the bond stress, as torch steel is having rough surface, so friction is more, so 60% we can increase the bond stress, and that is 470 470.1 mm. Now consider the third case. In this, given things are diameter 10 mm, Fe 415, M20, but this bar is under compression. For compression, we must increase the bond stress by 25%. So for M20, tau BD, we know that it is 1.2 Newton per mm square. Increase the 60%, increase 60% for torch steel. So 60% of 1.2 means it is 0.72, and increase 25%, increase 25% for bar in compression, or bar in compression. So 25% of 1.2, that is 0.3. See, this is 60% of what? 60% of 1.2, and this is 25% of 1.2. So total, what I will get? 2.2 Newton per mm square, tau BD value, and therefore LD equal to phi into sigma s divided by 4 into tau BD. Now phi is 10 into 0.87 Fy divided by 4 into 2.22. This is the corrected value of bond stress considering as it is torch steel and it is under compression. So LD we get 406.5 mm. So likewise we can calculate the value of LD. Now this completes the small chapter bond. Further, here we will see the anchorage value of bends and hooks. This is given in clause 26.2.2.1 of IS 456. The bends and hooks shall conform to IS 2502. For bends, the anchorage value of bend, see, the anchorage value of bend shall be taken as 4 times the diameter of the bar for each 45-degree bend, subjected to maximum of 16 times the diameter of the bar. Now, for example, if the bar is bent at an angle of 45 degree, and if the diameter of the bar is say 10 mm, then its anchorage value is equal to 4 times diameter of the bar, that is in this case 40 mm. So for each 45-degree bend you will consider 4 times into diameter of the bar. So if the bend or hook is suppose 90-degree, same suppose 10 mm diameter bar, and it is 90-degree, then anchorage value is equal to 8 into diameter of the bar, that is 80 mm. See, 4 times for each 45-degree. Here total 90-degree. So 45 and 45. So 4 and 4. So 8 times diameter of the bar. This is limited to maximum 16 times. 16 times diameter of the bar. So at the most you can bend like this in 180-degree. So in this case 45, 45, 45, 45. 4 times 45, it means 16 times diameter of the bar in this case. This is for anchorage value of standard hook. For 45-degree bend, it is 4 into diameter of the bar. For 90-degree bend, it is 8 into diameter of the bar. Maximum 16 into diameter of the bar you can consider as a anchorage value. So this completes the bond chapter. Thank you.